Welcome back, everybody. Last time, we saw how we could take a differential equation and by using a bunch of line segments, numerically get an approximation for a solution, right, once we have a chosen base point. Today, we're going to see one way that we can look to do better than an approximation. We're going to ask, how can we actually find exact solutions to a differential equation? Not just approximate, but formulas, get exact solutions. And it turns out that there's no one-size-fits-all answer to this. The answer is it kind of depends on what our differential equation looks like. And I claim that this is very similar to just regular old integrals. Right? If we're trying to integrate some function, compute antiderivatives, there's no one-size-fits-all technique for integration, right? We have a bunch of techniques on hand that we can look to use depending on what our function looks like and what that might be suggesting. Today we're going to look at one possible form of differential equations. If you go ahead and take a diff-EQ class, you'll see even more. The kind that we're going to think about are what are called separable differential equations. And these have a nice technique for getting solutions. All right, so here's the result here. If our differential equation is separable, and here's what that means. Essentially, it means, like in English, I'll say, can somehow separate the x and y stuff using multiplication and division. And how that looks formally is that our differential equation can be written as, so over here, here's our y prime, right, dy dx. Y prime equals something in terms of x times something in terms of y, or say something in terms of x divided by something in terms of y. The idea is we can separate our x stuff and our y stuff. And our formula here down below, this is actually kind of bouncing off of the second equation here. So let's say we can write our differential equation like this. The idea here is to then kind of treat this dy dx as a fraction of differentials. So in other words, let's treat the dy on its own and keep it kind of glued up there where it is. And let's multiply both sides by hy to bring that to the dy side. And then take the dx, multiply both sides by it to bring it to this side up here on the right. And then once we have that, our y stuff on the left-hand side and our x stuff on the right, we go ahead and integrate. And it turns out that what we get afterwards is an equation that implicitly defines our solutions. And implicitly here, this is really just indicating that our equation, we might not be able to solve for x. If we can, then that's great. Then we can find an explicit solution. But often, we just get an equation with some y's and some x's, and that's the best we can do. We get just a general equation implicitly defining our solution curves. All right, let's see how this goes with two examples. One just kind of abstract, and the other has some physical interpretation and meaning. All right, so at the bottom here, let's solve the initial value problem given by our differential equation here. And so that this language of solve the initial value problem, and what we're talking about is doing two steps. One is, solve the differential equation and get a family of solutions, right, where there's some c involved, involving some constant c, and then we want to figure out what c will make this initial condition happen. So those are our two steps. And what I claim is that our differential equation here is separable, that we can separate out the x stuff and y stuff. Now, you might not believe me because, hey, we got y stuff and x stuff all together inside this exponent, but here's the deal. We can separate it, right? Do you see how we can kind of break this up and separate our y stuff and our x stuff? If you're thinking rules of exponents, you are absolutely on the right track. Right? We can break this up as e to the y times e to the x squared, and with that, we've separated with multiplication our y stuff and our x stuff in our exponential, and we can work with that. All right, so here I've taken our y prime on the left-hand side and just rewritten that as dy dx for the sake of doing this separable diffeq process. So now the idea, recall, is to take our y stuff, and dy, kind of that stays where it is since it's in the numerator, it's on the ground floor. That's the y side on the left, so we want to take all of our y stuff, multiply it on over, so multiply both sides by that, and we'll take our x stuff and multiply both sides by the dx. Get that dx on the right, and then here I've also taken the e to the x squared, and to help ourselves out, I push that to the numerator, the negative exponent. Now, at this point, we've kind of brought our y stuff to their side, x stuff to its side. Now, we just need to integrate. Now, looking at our two sides here, we have two separate integrals to think about. We can just do so one at a time. How might we integrate both of these sides? So here we're going to have to use two different techniques. Over on the right, we can do a u sub. Over on the left, the u sub's not going to work out, but integration by parts. And since we have the y out front, we'll have to work through that. And so here's what that looks like. Here I didn't do a formal u sub. Over here, we could do one if we wanted to. We could also just kind of by hand figure out what the antiderivatives are going to look like. They're going to have this exponential piece just because of how exponentials work. And that's just going to be off by a scalar multiple. And in order to have the derivative of what we're getting down here match what we want, we just need a scaling factor of -1/2. All right, so that when we take the derivative, we get -1/2 times this times the derivative of negative x squared, and the -2, -1/2 would cancel. Just get left with x like we want. Or in other words, this is what we'd get through a u sub. Over on the right, working through the integration by parts, here's our first application, and then we're just integrating e to the y which just gives us e to the y. And if you work through this, you might have added the plus c on both sides. In general, we just collect those two constants over on the right and just write a big plus c, because a constant plus a constant is a constant. And so here we have a family of solutions. For each c that we want to pop in here, any constant, this equation here implicitly defines a solution curve to our differential equation. And it turns out that since we have y's in the exponent and on the ground floor, we can't solve for y in this situation. But in terms of solving our initial value problem, we can still find our constant c that makes that happen. And so here on the left, we're working through that. Our initial condition is that y of 0 equals 1, or in other words, right, if we plug in x equals 0, the y value that we got spat out needs to be 1. And so here we can take these two values for x and y and just pop them in to our family of solutions equation here. So if we plug in 1 for y, get this on the left-hand side, and for x, plug in 0. Things boil down nicely. And on the left, we just have e minus e, which is 0. And on the right, e to the 0 is 1. And so we're just getting minus 1/2. Add that over. We found what c makes that happen, solves our initial value problem. Now here we can actually use Desmos to get a look at what sort of curves are defined by our equation here, and kind of watch this initial condition get solved. Let's bring that up. So here on the left, I have our equation for our family of solutions, and here I made c a slider, and so as we move that slider to different constants, we see that we get a different solution curve, and they kind of look pretty different now. They kind of are gone. But we notice we get different looking solution curves depending on what our constant c is. So each one of these curves would satisfy our differential equation. If we had our direction field, all those little line segments on this plot as well, these curves would be moving through those perfectly. Now our initial condition, right, was x equals 0, y equals 1. In other words, to go through this point here. And here we can just visually spot check our c that we got. It looks like 0.5 is moving through that 0.01. And that's exactly the c that we found, right? 1/2. And so here we get visual confirmation of our work, which is nice. All right, well, let's look at another example. Let's solve the initial value problem, y prime equals ky. With initial condition, y of 0 equals y naught. Because why not? Well, here we have a lot of letters floating around. Let's just talk a little bit about this. So this k, this is just some number, and same with this y naught over here. These are some kind of set constants that we're just not specifying. Now, it turns out that this differential equation actually shows up pretty easily when thinking about population growth. Just kind of reading what this says, on the left we have y prime, or if we're thinking of y as the population size, then y prime is the rate of change of our population. And on the right, another way to say equals some constant times our population, you'd say is proportional to the population size. And this is often a physically realistic and reasonable assumption to make. And so our question here is, okay, based on kind of this, rate of change of population setup, what are the solution functions that satisfy this? And what I claim is two things. First of all, that this is a separable differential equation, so we can actually solve it. And more than that, more than just getting an implicit equation, we can actually solve what we get explicitly for our function y in terms of our input variable. And usually, if we're thinking about this physically, we'll use t to represent that input variable, just to think about that input as being time, so population varying with time. All right, pause the video and see how far you can get taking this separable differential equation, working through the separable process, solve afterwards for the function y, and then see which particular function is going to solve our initial condition. All right, well, let's walk through this one here. So first step is I'll just take our differential equation and I'll just replace the y prime with dy dt. And then our y side is on the left, and so I'll take the y and divide it over to the left and take the dt and bring it up, multiply both sides by the dt. And once we have that, we've got our y stuff on the left, or any t stuff, which we really don't have t showing up, on the right. Now, our task is to integrate. And on the right, just integrating a constant, so the antiderivatives are kt plus c. On the left, if we're being real careful, natural log of absolute value of y. It's our most general antiderivative. All right, collect our constants over on the right. And so here, there's choices of timing. If we really wanted to, we could use our initial condition, y of 0 equals y naught, at this point to figure out what our c needs to be. But let's not do that yet. Let's actually try and find our solution function explicitly first. Turns out it's a little bit of a cleaner way to do this one. All right, so if we want to solve for y, it's inside a natural log, and so let's exponentiate both sides. And over on the right, we'll be exponentiating that entire right-hand side. To get rid of the absolute values, well, if the absolute value of something is something else, well then our y in this case is either plus or minus that something else. And at this point, we have successfully solved for y. Is just hideous looking a bit. We can clean this up. We can actually use the same exponential trick that we used before. We can break this up as e to the kt times e to the c. And if we bring that e to the c over to the left, here is what we get, plus minus e to the c. And an observation is that this thing, plus or minus e to the c, is just some big ugly constant. Right? Once we choose a constant c, well then e to the c is a constant, and then either plus or minus that is still a constant. And so to just clean this up, let's just give that ugly thing a name, call it A. There we go. This looks a lot friendlier. And so here is our nice clean way of describing our family of solutions to our differential equation. And now we just can find out which one of these satisfies our initial condition. Y of 0 equals Y naught. And so the idea here is that, well, for our family of solutions here, we can take t equals 0 and plug that in, and we just know that what we get needs to equal Y naught. And so here we plug in 0 to our functions here, and so that t up top is just going to get replaced with 0. And so y of 0 is a times, it's going to be 1, which equals a. Right, that is what y of 0 equals. And from our initial condition, right, we need that to equal Y naught. And so actually right there, no more work needs to be done. We found what our kind of parameter needs to equal. It equals our initial value, Y naught. And so there is our particular solution to this initial value problem. And so what I'd like to do is just explore these a little bit using Desmos, see what these look like, and see what happens as we change these parameters. Let's bring up the same sheet. All right, so here I have our kind of family of functions. And here I'm just using a instead of y naught because this looks cleaner here. But here it's set to, a is set to 1, and this k is set to 1. And notice what function we're actually staring at this point is simply e to the x. Right? So here's our nice natural exponential function. And notice what happens is we take this a, or in other words our y naught, and move that around. Say if we set it to 5, that's just determining, right, what our solution curve's value is at 0. Right? And so thinking physically, this a is just our initial population for whatever population we have to be thinking about. That's what this a, or the y naught, represents. And so moving that kind of just slides our exponential curve so that it passes through that initial population value. Now k, on the other hand, if we increase that, that's going to give us a steeper slope. And if we decrease it, it's going to be a little bit less. This k is what's called the relative growth rate. If k is large, that means there's going to be, there's going to be more of the population that is reproducing, so you're getting a faster increase in the population. And if it's smaller, it means it's not going to be as great of a population increase as for each step forward. A little bit more mellow. And so a graph like this can show up, say, if we're thinking about populations. For example, if you have a petri dish with some bacteria, this is often a reasonable model for how that population grows. It's going to grow exponentially, at least for a certain period of time, right? And, what do these curves do as time moves forward? Well, the limit of this function as t goes to infinity is infinity. Right? These things blow up and never stop. And so, one of the things with mathematical models is they're just mathematical models. This model would predict that the bacteria would take over the whole universe and we'd all become those bacteria, right? that's not so realistic. There are other population models that sort of take some limited resources into account, and there's lots of different things that you can do in different situations. But each model will have situations it's useful for and not useful for, and so it's just important to know, I guess, the limitations of any particular mathematical model. Here, this is the basic shape that we get when that relative growth rate k is positive. If we make that negative, we get a shape like this. And this is also actually physically meaningful. This is where instead of your population increasing, your population decreases exponentially as time moves forward. And this can be the case if you're studying radioactive dating methods and things like that. If you have radioactive decay going on, this sort of model is used to model those sort of situations where you have a radioactive isotope and has a half-life and stuff like that. An interesting note is that if you have a really good memory, back at the start of chapter 9, we looked at actually an example of our differential equation, y prime equals some constant times y. Right, our differential equation we started with was y prime equals 1/2 y, and we've used that as our first example to play with direction fields and stuff like that. And so let's actually bring up that direction field here, and we can see now that these curves do move through that perfectly. So here, if we bring that up, right now, this curve is certainly not moving through this direction field perfectly. But notice the direction field is for k equals 1/2. And so let's move our k to be 1/2. There we go. There, that looks better. All right, now this curve is indeed moving through this direction field perfectly. And here, if we want, we can actually make our direction field interactive. Instead of 1/2, let's make it k. And now as we change the k, the direction field will change along with us and show us that indeed for each k, even negative k's, our curve is moving through that direction field. Ooh, that's pretty mellow. Too close to 0. There we go, moving through the direction field perfectly. And that still holds true if we move our initial population. Right? Physically, it doesn't really make sense to have negative initial population, but mathematically, it's all good. All right, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.